Hi everyone, Carrie Jansen here. Stereochemistry is currently on hiatus, and this month we're sharing a pair of episodes of Distillations, a podcast from the Science History Institute. Distillations explores stories from the intersections of science, history, and culture. The episodes we're sharing with you here are all about rare earths, the collection of 17 elements that have become indispensable components in many modern technologies. And to help me introduce this story is C&EN reporter Mitch Jacoby. Welcome, Mitch.
Hi, Carrie.
Mitch, what should we know before we dive into this episode?
Right. Well, as we'll hear in this story, lots of critical technologies depend on rare earths. You're probably aware that rare earths are used to make electronic components for smartphones, but what you may not know is that they're also used in medical imaging devices and some green energy technologies like wind turbines. And besides those applications, they're also used in disk drives, electronic displays, lasers, electric car motors, and catalytic converters. These elements are so useful because they have unique electronic and magnetic properties. The Distillations hosts describe them as magical, and I don't think that's far off. They're really fascinating and useful materials. But getting them out of the ground and into our gadgets is no small feat. And so after we explore the magic of rare earths, we'll also hear about the hidden costs of rare earths and what scientists are doing to try to find a way to produce them sustainably.
Both Part 1 and Part 2 of this story are now available in Stereochemistry's feed. And if you like what you hear, you can find more great stories from Distillations on your favorite podcast platform or at distillations.org. We hope you'll check them out.
I learned some really neat things from this story. Part 1, which we're about to hear, opens with an interesting story that I actually never heard before. We'll hear about how a Chinese fisherman's encounter with the Japanese Coast Guard triggered a global awakening to our dependence on rare earths.
And now, without further ado, Part 1 of Rare Earths, The Hidden Cost to Their Magic by Distillations.
Hello, and welcome to Distillations, a podcast powered by the Science History Institute. I'm Alexis Pedrick.
And I'm Lisa Berry Drago.
In each episode of Distillations, we take a deep dive into a moment of science-related history in order to shed some light on the present.
Today, we're talking about rare earth elements, and this is a big story, so we broke it up into two parts, both of which are available right now.
In Part 1, we're going to tell you about the magic.
And in Part 2, we're going to tell you about the costs. Chapter 1. The Fisherman.
On September 7, 2010, a Chinese man fishing near disputed islands in the East China Sea set in motion an international crisis, with effects that would be felt around the world. Here's what happened.
Is this the moment of maritime drama which sparked the worst political row in years between China and Japan? A Chinese-marked fishing vessel is ordered to stop by Japanese sailors.
The Senkaku or Diaoyu Islands have periodically been a source of geopolitical tension between China and Japan for years.
The islands are uninhabited, but they're claimed by China, Japan, and Taiwan. China and Japan have a peacekeeping agreement that says no one from either country is allowed to get within 12 nautical miles of the islands.
And if someone did get within 12 nautical miles of the islands, then it would be the responsibility of whichever Coast Guard was patrolling at the time to escort that person back out into international waters.
This is Julie Klinger, a geographer and an assistant professor of international relations at Boston University. The agreement she described sounds simple enough, but things got complicated for the fisherman.
This fisherman had gotten a little too close to the islands. His name is Zhang Qixiong, and instead of complying with the routine escort back out into international waters, he instead rammed his fishing vessel into a Japanese Coast Guard vessel, and because of this, he was detained.
The Japanese voices apparently warn that the Chinese captain is turning towards them, and they brace for impact.
When news of the arrest hit Chinese and international media, the part about him ramming his boat into the Coast Guard was left out, as was the fact that he was drunk.
And so what it actually looked like at the time, in September of 2010, was that Japan detained an innocent Chinese fisherman. And this was interpreted in China as an act of escalation. And so this took on a real big significance, I think, far beyond what the actual incident called for. And so, Beijing was working with authorities in Tokyo in order to secure the release and the repatriation of Mr. John. Meanwhile, the public wasn't really hearing a whole lot about this, and there were several people who felt like Beijing was not responding appropriately enough.
People were angry, and some of them decided to take matters into their own hands.
There have been nationalistic protests in both countries. In China, some have turned violent, despite efforts by security forces to keep them under control.
But one way that a handful of people decided to teach Japan a lesson was actually by withholding exports bound for Japan. It just so happened that some of these exports were rare earth elements.
If you only have the vaguest idea of what rare earth elements actually are, or if you've never heard of them at all, you're not alone. And in September of 2010, most people around the world were in the same boat. That was all about to change.
Fall of 2010, the whole world wakes up to our reliance on rare earth elements.
Rare earth elements are often called the spices or the vitamins of industry. Because while we don't need them in large quantities, they're in pretty much everything we associate with our modern world.
My favorite metaphor is that they're like yeast in pizza. You only need a little bit of it, but without it, there's no pizza.
Another way to say it is that rare earth elements are essential for both the hardware and the software of life as we know it.
They power our iPhones and computers. They're in wind turbines and hybrid cars and power windows. They're in dental implants, X-ray machines, life-saving cancer drugs.
That shipment that was held back in China by just a handful of people could have contained anything. But it happened to hold rare earth elements, the essential tiny components that make our modern lives possible.
Nobody really knew or even really missed the fact that these shipments of rare earth elements had been held up until Japan's customs authority inquired at China's customs authority what happened to the ships. And so people start asking questions. Word gets out that some brave Chinese nationals are teaching Japan some humility by reminding it of its economic dependence on China.
And then the story sort of took on a life of its own.
China surprised governments around the world by halting shipments of something called rare earths.
International concern soared higher on September 22nd when China stopped all exports to Japan following the arrest of a Chinese fisherman in disputed territorial waters amidst rising tensions.
A lot of people had to learn a lot of things very quickly. First off, what are rare earth elements? Why are they important enough that China would embargo these things against Japan? And why does that matter?
People began making obvious but incorrect conclusions. Like, for example, this one.
So these things called rare earth elements are being embargoed by China. That must mean they're rare.
And the fact that in 2010, China produced 97% of the world's rare earth elements led to another obvious yet incorrect conclusion.
Oh, China produces the most rare earth elements because China has the most rare earth elements.
And all of these assumptions led to a big, frightening conclusion that China was holding the world hostage through its supposed rare earth embargo, that China was engaging in some kind of economic warfare.
This was the narrative that blew up overnight, and of course the markets reacted accordingly. The prices for certain rare earth elements increased by more than 2,000%.
The fishing boat incident had worldwide implications.
This unleashes a gold rush. All of a sudden, everybody is looking for rare earth elements. So there's a sort of swashbuckling like gold rush sensibility that was really fed by the 2010 crisis.
But you're probably still wondering what this really has to do with you. Why should we care so much about rare earths?
Like we said earlier, our entire modern world is made possible by this collection of elements, 17 in all. 17 elements that are sprinkled in small amounts through some of our most powerful, futuristic, and dare we say it, magical tools.
While we don't need much of them, rare earths are what make the magic happen. They have unusual magnetic and electrical properties that make our stuff faster, stronger, and lighter. And we've been coasting along, enjoying their magic for a while now. In fact, we've come to expect magic. Nothing less than magic will do. And if you're a sci-fi and fantasy nerd like me, you already know what comes next. It's the twist that the evil wizard doesn't recognize until it's too late. Magic always comes at a cost.
For us, the cost of our magical devices and technology is environmental devastation. And it's a big cost, but it's invisible to most of us in the Western world. So we didn't even realize we were paying for it at first. Back in September of 2010, when a Chinese fisherman rammed his boat into a Japanese Coast Guard ship, it didn't just make us all aware of the existence of rare earths. It started making us aware of their price tag.
And it turns out that magic is usually better left a mystery. Because when you pull back the curtain, it's usually complicated and ugly. But we're Distillations, and pulling back the curtain is what we do. So here we go, starting back at the beginning.
But first,
Chapter 2, a brief rare earths primer.
We realize that if you're listening to this podcast, it's entirely possible that you are familiar with the periodic table. Maybe you've looked at it on occasion, maybe more than one occasion, even numerous occasions since 11th grade. But for those of you who have not, we see you, we love you, and you're not alone.
So on the periodic table, you've got all the elements sorted together into groups. Things that have similar characteristics are near each other. Like, for instance, the elements in group 1 are the alkali metals, or, as I learned them, the things that explode if you drop them in water.
The rare earth elements are mostly in group 6. They're generally silver, silvery white, or gray metals. They're shiny until they hit the air, when they tarnish. They also have high electrical conductivity, and this is where the magic comes in.
One of the most important applications of rare earths are in magnets. The magnet basically changes electricity into motion. The stronger the magnet is, the more motion you can get. So a strong, tiny magnet can make your iPhone vibrate itself off the table. And the same idea works backwards, too. Magnets make it possible to change motion into electricity. Like when the shaft of a wind turbine spins inside a magnetic field, it becomes an electrical generator.
And as scientists started discovering in the 1980s, you can make really strong magnets when you combine small amounts of rare earths, like neodymium and dysprosium, with metals like iron and boron. These powerful, permanent magnets are partly what allows our gadgets to keep getting smaller and smaller and smaller.
Rare earths aren't radioactive, but they're often found in rocks alongside radioactive elements. And this is the big thing. They're hard to separate from other metals and elements around them. Instead of thinking of it like panning for gold, where you can just wash off the dirt and boom, you're done, getting rare earths is more like Play-Doh.
Yes, Play-Doh. Stay with us. Picture a bunch of differently colored pieces of Play-Doh. If you've ever watched a kid mush them together, you know how hard it is to separate those colors back into their original containers. So that's what it's like when you find rare earths in the ground. That's a bit about what they are, but perhaps more important is also what they're not.
Despite their name, they are neither rare nor earths. At least not in the way we use that term now. And that's part of the problem. In the 18th century, when they were discovered, people understood rare to mean new. And earths was because before we understood electrons and atomic weight, we classified elements by their properties: gases, metals, nonmetals, and earths.
In some ways, they're actually the opposite of rare. They're everywhere. But while they're spread roughly evenly over the surface of the Earth, it's hard to find a lot in one place, and extracting them is like trying to pull apart that ball of Play-Doh. They're jumbled together with lots of other minerals in different concentrations. And thus ends our brief rare earths primer. Now that we're all back on the same page, back to the story. Chapter 3, The Excitement of Discovery.
Even though it wasn't until 2010 that most of the world realized our dependence on rare earths, they've been around for a lot longer. Charlotte Abney Salomon is a research fellow here at the Science History Institute and an expert in 18th century Swedish mineralogy. And Sweden happens to be the place where the first rare earth element was discovered.
I have made a pilgrimage to the quarry in Ytterby, where the original stone was found.
Ytterby, Sweden is a tiny island off Stockholm. It's sometimes called the Galapagos Island of the periodic table because 7 elements were discovered there. 4 of them are named after the island.
In the 1780s, a Swedish artillery officer who was highly educated in chemistry was looking at some of the rocks that had been found and identified one rock that was unusual. And it found its way to a chemist by the name of Johan Gadolin in Finland, who analyzed it to see what was so unusual about it.
It was a rock unlike anything he'd seen before. And Gadolin got credit for discovering a new type of quote-unquote earth. The excitement was mainly that it was new, but the rock didn't really do anything. It wasn't magic yet.
The nature of their chemistry means that they behave very, 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 very similarly. So they really do appear as one pure substance. And so over the years, they were able to assess them with finer and finer distinction and actually make the distinction between these elements.
At the turn of the century, Swedish natural historians were obsessed with cataloging and categorizing nature.
Practicality is absolutely a stereotype of the Swedish character, and it's as a scientific community, they absolutely went very, very deep over a very long period of time in attacking this question.
And mineralogists were also obsessed with the idea of chemically analyzing every new rock they found on the ground. So they separated out rare earth elements and began to organize them. The first rare earth they identified would eventually be named yttrium. The second, cerium.
Then lanthanum, didymium, which, turned out to be a mixture of praseodymium and neodymium. Then yttrium, erbium, and terbium. Then Lars Friedrich Nilsson, another Swede, detected an element in 1879, which he called, wait for it, scandium. After Scandinavia.
So one by one, the rare earths are discovered, until finally there are 17. The only problem was that no one really knew what to do with them.
I have seen a periodic table from about 100 years ago that says rare earths, and it has an asterisk and says they're so rare and so unimportant that we won't be naming them here. And so certainly 100 years ago, they were definitely considered just kind of trivia of the periodic table.
So the years go by. Like 100 of them. And there's lots of discovery, but no application. Until
a chemist went looking for some magic.
Hey listeners, we just want to take a moment and remind you to check out our website, distillations.org.
That's right, because Distillations is more than a podcast. We're also a multimedia magazine.
We tell stories about the intersections between science, culture, and history.
You can read about the pain-relieving potential of hot peppers.
You can watch a video about an interactive astronomy textbook from the 17th century.
And you can find every single Distillations podcast episode ever.
Also, you can find episode transcripts and research notes, all at distillations.org.
Back to the show.
Chapter 4, Karl Auer von Welsbach and the Mixed Up Metal.
It's not until the 1890s that any of these elements become commercially useful.
Roger Turner is an historian and research fellow here at the Science History Institute. He's telling us about Karl Auer von Welsbach.
Welsbach was a German chemist. In 1880, he was at the University of Heidelberg, studying under Robert Bunsen. of the Bunsen burner. Yeah, that guy, the one who invented it. In 1882, Welsbach went to Vienna, where he worked as an unpaid lab assistant doing chemical separations of, what else? Rare earth elements.
But Welsbach had dreams. He wanted to be a powerful wizard, industrial tycoon. But there was only one problem. In the 1880s, big business was in lighting. And one guy named Thomas Edison pretty much had that on lock. So Welsbach had to come up with something else. And he did. Better streetlights.
Urbanization is going gangbusters in the late 19th century. There's more and more people are moving into cities.
And those people wanted the streets to be lit at night. And Welsbach makes their wishes come true. He creates the gas mantle. It's basically a fabric bag that creates light when it's heated by a flame. And it's powered by 1% thorium and 99% cerium, a rare earth. And there it is. Magic.
His lights became big business. By the 1930s, Welsbach's company has made 5 billion of them. And he's made a ton of money, which, let's face it, is one of the higher forms of sorcery. But there's a problem with his process.
He's left with this kind of great piles of waste materials, which have this annoying tendency of catching on fire. So he put 2 and 2 together and realizes that perhaps he can use the waste metals as part of a fire starter.
He calls the leftover material Mischmetall, or mixed up metal, and with it, he makes a model of the modern cigarette lighter.
But remember, magic has a cost. All these brightly lit streets and cigarette lighters weren't free.
The first cost came from mining the ore. To extract the rare earths needed to make the gas mantles was no easy process, and it did terrible damage to the water supply.
Anytime you're mining, basically the acidic water that reaches groundwater or flows into streams, that can poison streams and kill off the animals and the plants that are in those streams.
Refining rare earths caused other problems. Acid baths and radioactive materials were involved. But at the time, these costs were hidden to Western consumers because they were happening in faraway places like Brazil, India, and South Africa, places that the European nations using the materials had colonized.
As nifty as streetlights and cigarette lighters are, rare earths still hadn't permeated our lives yet. For that to happen, we've got to fast forward to the Cold War. Because what's a history of science story without a chapter on the Manhattan Project? Chapter 5. From Uranium to Color TV.
So the history of rare earth elements is tangled up with radioactive elements, because rare earths themselves are literally, physically tangled up with radioactive elements. That's one of their defining characteristics, that they're bound up in deposits alongside things like uranium.
So when the Manhattan Project needed uranium for the bomb during World War II, it makes sense that they asked for help from one of the few rare earth chemists in the U.S.
After World War II, the U.S. saw uranium as crucial to national security. Uranium made the bomb, and other countries had to join in the arms race. They also wanted it for nuclear power.
Their goal is to find uranium wherever it can be extracted around the world, and first use international sources as much as possible while preserving domestic deposits for future use in times when perhaps international trade is disrupted.
And this sets off a wild moment in U.S. history. If you can imagine it, it's the late 1940s. The U.S. Atomic Energy Commission announces it will buy uranium ore from any American who finds it. It set off a uranium gold rush.
They found uranium beyond their wildest dreams. They were so successful.
This uranium boom was one of the greatest mineral hunts we ever had, funded by the government, and I don't think we'll ever see anything like it again.
I know you'll be hugely surprised to hear that the Public Uranium Prospecting Initiative did not go very well. Newspaper accounts described cattle stampedes, people threatening each other with guns. Some prospectors were mining without protection and inhaled radioactive dust. The U.S. government decided a little belatedly that they shouldn't encourage amateur mining anymore.
One professional mine did open in the Mojave Desert in Mountain Pass, California. The mine was operated by a company called Molycorp, and at first, rare earths were kind of a sideline business for them. But that all changed in the 1960s.
This is a world of color. and the men of television long dreamed of capturing the full paint pot of nature and brushing it on the screen.
Color television was dope. But the red color on screen could only be produced by the rare earth element europium.
Color TVs became big business. And the Mountain Pass mine was the largest supplier of rare earth elements to the world from 1960 until the 1990s. All thanks to color TV. Because once you have color, you can't go back to black and white. First it's magic, then we expect it, and then we can't live without it.
But there's a cost.
There's always a cost.
And this time, the cost was a lot more visible because it was happening in our own backyard. Just like with Welsbach's gas mantles, the europium had to be bathed in acid and heated up in high temperatures. That's what separated it from the rest of the Play-Doh ball.
So this produces a lot of waste. It produces huge amounts of radioactive water, and it produces a lot of acid byproduct as well.
Common strategy to deal with all this contamination is to use something called a tailings pond. They're basically giant pools of particles from a mine, mixed in with chemicals and water to separate the stuff that you want from the stuff that you don't want.
But these tailings ponds leak and poison the groundwater. And so that's the kind of repeated violations of California environmental law regarding the poisoning of groundwater that eventually played part of the role in shutting down the Mountain Pass mine.
Federal investigators found that there were more than 60 spills of radioactive water that seeped into the desert floor. Eventually, the mine closed in 2002.
But of course, this didn't mean we were all ready to give up the magic. You know already, that's not how this story ends. Rare earths become an even bigger part of our lives.
How did we do it? By getting someone else to make the magic. You see, something else contributed to the California mine closing. China was quickly becoming the biggest rare earth supplier in the world, and neither Mountain Pass nor the U.S. as a whole could keep up.
Find out what happens next in Part 2, available now.
Distillations is more than a podcast. We're also a multimedia magazine.
You can find our podcast, videos, and stories at distillations.org.
And you can follow the Science History Institute on Facebook, Twitter, and Instagram. This story was reported by Rigoberto Hernandez and produced by him, Mariel Carr, and myself.
And this episode was mixed by James Morrison. For Distillations, I'm Lisa Berry Drago.
And I'm Alexis Pedrick. Thanks for listening.
You've been listening to an episode of Distillations, presented by Stereochemistry. You can find part 2 of this story in the Stereochemistry feed now. Stereochemistry is the official podcast of Chemical and Engineering News, which is published by the American Chemical Society. Thanks for listening.